myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. In today's video lecture, we will understand the Z transform concept from signal system from the AKTU syllabus, that is defined as subject code KEC 403. So here we will discuss the properties of Z transform. So Z transform, as we know, it is also defined as a tool to analyze the discrete signal in frequency domain or in Z domain. So for discrete signal, we need to calculate the Z transform, right? Coming to the first property for the Z transform, that is linearity, the linearity property. So what is linearity property? If the Z transform for x1n is x1z and the region of convergence is R1, okay, and if Z transform of x2n, the region of convergence being R2, okay. So what should be the Z transform of the coefficient multiplied by x1n plus the coefficient multiplied by x2n, okay. We can write by the property directly that it should be A x1z plus B x2z, okay. B x2z. Now this is one point. Next is Z transform cannot be defined without the region of convergence. So it is important to define the ROC in the Z plane whenever we are calculating the Z transform. That's important. So what will be the ROC of this particular? The ROC for this will be R1 intersection R2. Right, this is the ROC for the Z transform for which the linearity property is well suited. Next, there may be some exceptions for the region of convergence when any pole gets cancelled out. So the ROC may expand in that case. As we have seen in the Laplace transform properties also, this is happening in few cases. So for that, to understand this concept in more detail, we will have the numerical, that is xn a raised to the power n un minus a raised to the power n un minus 1. Let us calculate the Z transform for this. So as we know, xz is summation, okay, okay. So we will calculate the Z transform for an un, that is xz will be equal to summation n is equal to minus infinity to plus infinity an un z raised to the power minus n minus, as the linearity property holds, summation n is equal to minus infinity to plus infinity a raised to the power n u n minus 1 z raised to the power minus n. So let us solve this particular. We will get this un. This un is from n is equal to 0 to infinity, it is 1. What about this un? This is from n is equal to 1 to infinity, this is 1. So this is 1 for this range and this is 1 for this range. So my limits will get changed. So we will write summation AZ minus, according to the linearity property, n is equal to 1 to infinity. Here this is okay. Let us calculate this. This will be 1 plus AZ plus A so on minus from here the second summation that will be starting from this is not AZ inverse, that should be just a second. Just a second, there is some error in this first. Let us discard that error. Just a second. The minus power is not with, so here this is a raised to the power n and this is a raised to the power n, z raised to the power minus n, like this. Okay. So here from this, if I extend this 1 plus AZ inverse plus AZ inverse raised to the power 2 and so on, like this. Similarly here that will be AZ inverse plus AZ inverse power 2 plus AZ inverse power 3 plus and so on. So is this, I can write it as 1 upon 1 minus AZ inverse and minus AZ inverse common 1 minus AZ inverse. So here this 1 minus AZ inverse upon 1 minus AZ inverse, see, this is coming out to be 1. Now, in the beginning, what we were discussing is the ROC for the linearity property should be intersection of the two. But if I consider the ROC for this, if I consider, then please listen here that this ROC, if I make for the first term R1, for the first term, let's say this ROC I will consider as R1, this ROC I will consider as R2, and if I plot this R1 on the Z plane, So this is my unit circle obviously. Let's say A is less than 1. So this will be, let's say this is A, then my ROC would be mod Z greater than A. And the same ROC is for R2. And this is my unit circle. So this ROC is for these two. But what is the point mentioning here is, but here my result is coming out to be 1. Just a second. So here my result is coming out to be 1. So this ROC is entire Z plane. Isn't it? So in this particular example, we can see very well the ROC is extending. ROC is extending from mod Z greater than A to the entire plane. And why it is happening? See, what is the reason? Because this pole is being cancelled by the 0. So, and hence we can prove the linearity property is that ROC is intersection of the two, but there are some cases where ROC can extend. Okay, so this is the first property for the Z transform. Now coming to the next property, that is time shifting property. So for the time shifting property, if I am having one sequence xn, the ROC is R and the Z transform is xz, and if I shift my sequence to some n naught, then my ROC is same, but the Z transform will be Z raised to the power minus n naught multiplied by xz. So here this is getting multiplied, okay, but in this also we need to take care of the ROC, because maybe there are some cases while I am multiplying by this particular quantity, then it is possible that it can add or it can delete some points specifically at z is equal to 0 and z is equal to infinity. So as we understood in the case of linearity property of the Z transform, we will understand this time shifting property in point of ROC, that the examples would be, let us take the Z transform of xn del n minus k. So we have del n. The Z transform is 1. Okay. So for del n minus k, from the property it should be Z raised to the power minus k into 1. Okay. The ROC in this case is entire Z plane. Okay, but ROC in this case will be entire Z plane, but not at Z is equal to 0, because As you put z is equal to 0, the terms the xz becomes infinite and undefined. Okay, so that's why it is possible that some addition of or deletion of z is equal to 0 and z is equal to infinity may occur while we are applying the time shifting property in the z transform. Similarly, as in this case, the xn is equal to del n plus k. So the del n z transform is 1 del n plus z transform is the ROC is entire z plane, and in this case the ROC will be is entire z plane, but we will mention here except z is equal to infinity. So the ROC may get changed while calculating or applying the time shifting property. Scaling in the z domain. Next property. If the z transform for xn is xz, the ROC being r, and z naught raised to the power n xn, the z transform will be in this case x of z upon z naught. This term is getting divided. Okay, this term is getting divided. Please, this particular, you need to remember this particular thing, that z raised to the power z naught n, if getting multiplied, if I am scaling my sequence, then this is the total z domain is getting scaled, and the ROC will be mod of z naught into r. Okay, so that's also one important property. Now coming to the time reversal. For time reversal property, if the z transform of xn is xz with some ROC r, and I am reversing my sequence, the reversal has been applied to the sequence, then the z transform in this case will be x of 1 upon z. So the ROC, now coming to the ROC, which is very important point as far as we are considering the z transform. So for that case, if mod z is lying between a and b, let's say the ROC for this, for xz was some value lying between a to b, that means if I make the diagram for this, so I will make it, this is some unit circle. Okay, this is A, and this is B radius, and the ROC is so what would be the ROC of the reverse sequence? So the reverse sequence, the ROC will be 1 upon R by this. That means now the new ROC will be mod Z 1 upon B. Okay. Mod Z greater than 1 upon B and less than 1 upon A. And this is applied for time reversal property. The ROC is getting changed by this. If I want to draw this, so we can draw this also. The new ROC will be this circle is of radius 1 upon A and this circle is of radius 1 upon B. Unit circle is somewhere here and the ROC will be will be the ROC of the reversed sequence. Okay, so the thing is, whenever we are applying the properties, it is very important to take care of the region of convergence, because the region of convergence is another very important parameter which is to be considered always. So this is the time reversal property, and thank you for this particular lecture.